This is absolutely a high point of this cosm and many other cosms because we have an ultimate cosmic figure from the field of computer science and artificial intelligence and physics and math, and he's just a complete polymath and visionary, Stephen Wolfram of Mathematica and Wolfram Alpha and Wolfram language, and this great book. It's about, which you all have, which is, I think, 100 pages or something, and it completely distills lucidly and compellingly how ChatGPT works and why it can't really think. So it's going to be exciting to have Stephen Wolfram, a great titan in the field, here at COSM 2023. Thank you.
We're dying to get to the ChatGPT question, but before that, could you tell us, remind us all a little bit about your life as a physicist and as an entrepreneur in creating Wolfram Research, and then we'll get over to ChatGPT later. Okay.
All right. Little bit of the life story from I started out. I grew up in England. I got interested in physics when I was pretty young, so I was a fairly serious teenage physicist, and kind of figuring out things about particle physics, which was I got into that in the late 1970s when particle physics was kind of in its golden age. Always a nice thing, some field has some new sort of methodological advance, and for 5 or 10 years, there are all kinds of low-hanging fruit to be picked. I happened to get involved in particle physics at the time when that happened. I also discovered pretty early in my life, when I was 12, 13 years old, which is too long ago now, that computers were a useful thing, and that you could use computers to figure out things in physics. And for some strange reason, which I still don't really understand, other people just didn't realize you could use these tools to sort of extend what you yourself could do. So anyway, I got involved in using computers and doing physics and figuring out things about particle physics and cosmology and things like that, and wound up getting a physics PhD from Caltech when I was 20 or so. And then right after I got my PhD, I was like, okay, I've figured out some things about physics and so on. I've used a bunch of computer tools other people have constructed. This was 1979, and I want better tools. And first I tried to convince the people who'd built those existing tools, make version 2, but they said, oh, we don't want to make version 2, or it isn't possible to make a version 2. So I kind of decided to build my own software system for initially sort of doing computations that would be relevant for physics. And I kind of, thinking like a physicist, I kind of tried to take this question about how do you do computation, sort of drill down to find the most underlying primitives of this idea of computation. And that led me to build my first big computer system called SMP, Symbolic Manipulation Program, back in 1980 or so. I then sort of backed into, at that point, I was a faculty member at Caltech, and I kind of got backed into starting my first company, which was a traditional, I would say, venture capital funded, wasn't yet so traditional because those were early times, software company, and which I learned mostly from that I maybe wasn't as clueless about businesses as I thought I was, but then went back into doing basic science and kind of got interested in this question of how does complexity arise in the natural world, and realized that this kind of approach to science that we've taken for the last 300 or so years of saying, let's write down a formula for how things should work in the world, wasn't the only thing we could do. And we could instead think about programs as models for science. And that led me to kind of exploring, what do simple programs do? It's kind of eventually I wrote this big book called A New Kind of Science, but that's kind of what this is about basing science not on mathematical equations, but on programs. And so did that for a number of years, and kind of built up this field, which I guess these days, complexity theory is its typical name, although it's gone off in directions I don't really necessarily think are the right ones. But this question about simple programs out in the computational universe, what do they do? And the big discovery that I made was that even very simple programs can do very complicated and very interesting things.
Yeah.
Then
Like number
I kind
30,
of,
like number 30?
what's that? Rule 30. Yes,
Rule
my
30.
all-time favorite. It's kind of the very simple rule. It's just a bunch of black and white squares laid out in a grid, and you just have this rule that says, going down the page, color the square, next square, according to some very simple rule based on the color of the squares above it to its left and right. And that very simple rule is enough to give you this really complicated pattern that looks in many ways random. And that's kind of like what happens in a lot of nature. There are very simple underlying rules, yet the overall behavior that you see is very complicated. And this is, I think, it's a sort of a core phenomenon. It's the secret that nature has. It's also a thing that shows you that even though you know the rules for something, you don't necessarily know what's going to happen. And that to me is a really important scientific principle. It's a principle that actually I think has also societal implications, because it's kind of, in the end, it's the story of we set something up computationally. We know its rules, whether it's an AI or just a computational system. But just because we know its rules doesn't mean we know what it's going to do.
Yeah.
But in any case, back just to finish my sort of life story, I suppose, this is very long and ponderous. I'm sorry. I've had a complicated life. What can I tell you? So I kind of was interested in the sort of the new kind of science that you can build by studying programs rather than equations. But then I got interested in, okay, now I want to really build the computer system that I can use for the rest of my life to go figure out things, and hopefully for other people to figure out things. My first company by this point was actually doing okay, but doing things I didn't think were very sensible. Eventually it went public in a very undistinguished IPO a number of years later. But at that point, I kind of got started on what is now my current company back in 1986, Wolfram Research. And my goal was to kind of build a software system for sort of, as I would say now, making the world as computable a place as possible, finding a way to kind of represent things computationally, finding a way to take the kind of the things that we want to think about or compute about and represent those in a way so that we can actually do these computations. I kind of see this as being my modern version of this. It's not what I would have said back 35 years ago, but 35 years ago, I would have probably emphasized the application of what we were doing to areas like mathematics, being able to do mathematical calculations, sort of like humans with algebra and things like this, but automatically. Today, what I would say is that I kind of see there as being these several stages of formalization of the world. Yep. From kind of just, we use human language, we refer to things by words rather than just pointing at them, then to things like logic, where we can have a sort of more formalized version of how we talk about things, to mathematics, or we formalize further to computation, where we're kind of trying to describe the world, whether we're talking about cities or chemicals or mathematical formulas in a computational way, so that we can kind of think about them computationally and have our computers help us to compute things with them. And so for the last 35 years, we mostly built this system now called Wolfram Language, which is this computational language for kind of representing the world and computing things with it. And I'm happy to say that an awful lot of interesting inventions and discoveries have been made in the world with what we built. And I would say that sort of the goal is, programming languages operate at the level of sort of poke the computer to do what you want at the level of the computer. What we've been interested in is how can you represent the world as humans think about it in a computational way, so that we can have sort of a notation to crispen up our thinking, and so we can have the computer help us to figure things out. And part of the goal of our computational language is to build in as much as possible of not only the kind of algorithms that we know in the world, but also knowledge and actual data and so on about the world. And that's been something that I would say has been very, very successful. And it's kind of it's a little bit of a strange situation, because people who think of themselves as kind of just programmers aren't as big users of what we built as the people who think of themselves as CEOs and CTOs and intellectual leaders of various kinds. They use our product often all the time, every day,
Yeah.
because it kind of gives them this superpower to go from things they're thinking about to actually being able to sort of automate their implementation.
So
It's a little
now-
bit different from a typical programmer who's kind of given the set of things that they're supposed to write code for, and the moment where they kind of rethink about things computationally is a rare thing.
So you're
just
looking
to
for-
finish the one last.
But you're
Sorry,
look-
I'm.
Yeah, go
You're
on.
Go for
looking,
it.
you're looking,
Yes.
I've been given permission to interrupt you occasionally.
Please, absolutely. Otherwise I'll yak on in a terrible monologue.
So
please.
you're on a quest,
I wish I could see you as well as hear you, but I can
You
hear
can?
you. Yes.
you're on a quest to find the code that generates the universe. Will that code be written?
That is
Will that code be written in Wolfram language?
certainly could be. I mean, the way I've been looking for it, it's all represented in that form.
Yeah.
I mean, just to say something about that quest, given this discovery that simple programs can do really complicated things, the ultimate version of that is, can we make a simple program that is our universe? And I first started thinking seriously about ways to do that in the early 1990s, made some progress, then kind of put that aside, partly because my friends in the physics community were like, oh, we don't need any new theories, we're good, we're going to figure this out ourselves. Well, they didn't do it. So then about 5 years ago now, some young physicists who'd kind of learnt the things I'd done when they were in like middle school or something said, you've really got to finish this, you've really got to make progress on this. And so we started to do it, and it worked just unbelievably much better than we had expected. And we kind of, I think, can say now that we're pretty sure we know kind of the machine code that underlies the universe.
This is the physics
And
project.
just to give you some sense of
This is the physics
what that
project.
this is our physics project. Our what I'm referring to as our physics project, which sounds like kind of a kid's physics project, but this is I think a grown-up physics project, so to speak. And it's kind of the place it starts is the fact that space. What is space? And one of the big discoveries of physics from basically a bit over 100 years ago was matter is discrete. It's made of discrete molecules. Light is discrete. It's made of photons. Space, on the other hand, people have always assumed, although they've argued about it from time to time, but they've always assumed is continuous. So you can like put things any place you want in space. The big thing that our models start from is the idea that no, that's not true. Space, like other things, is discrete. It's made of sort of discrete atoms of space. Those aren't atoms like atoms of matter. They're just sort of elementary points. And the only things we can say about them are kind of how they're related to other points. So we build up this giant graph, this giant network of the relation between all the atoms of space. And there are probably maybe 10 to the 400 atoms of space in our universe today. And then, so everything about our universe is represented by the structure of this network. And it turns out that the sort of one of the early big discoveries is that the gravity and the structure of space-time are sort of necessary emergent features of the structure of such a network when it behaves in particular ways. And then the next kind of big discovery is that quantum mechanics is sort of an inevitable feature of this kind of system. And I mean, this is a big story, but in the end, what we realize is, again, this is going deep in a rabbit hole, and I'm happy to go into this rabbit hole, but
No, but it's time now to shift you over to chat. How does
So compared to what you're doing, that sounds strikes to me as the real artificial intelligence that actually yields correct answers. Here you're writing about ChatGPT that has to offload its difficult questions to Wolfram Alpha to get correct answers. Why do we need ChatGPT?
Well, so the big achievement and the big surprise is that we can have a system that fluently produces and understands human language. It wasn't clear how difficult that was going to be. It's one of the things that we thought is the coolest feature of what brains do. And we didn't know whether brains needed to have some fancy new piece of physics and so on to be able to operate the way they do. It was a big surprise a year ago now when it became clear that just a neural network, just a computational system could generate kind of fluent chunks of human language. We didn't know that was possible. And I think the thing to understand is when you sort of start saying, well, why does that work? How does ChatGPT actually work? It, like many of these things, it kind of becomes less mysterious when you can kind of, when you understand more about how it works inside, but it's still mysterious that it works. It's still not obvious that it would work. And it's kind of a scientific discovery that it's possible to have a thing like ChatGPT that can produce this thing that's one of our sort of prize features, namely human language. And I think just to say something about sort of how it works and how to think about it, perhaps, when you're kind of inside ChatGPT, what is it doing? Well, you give it a prompt, you give it a piece of text, let's say, the cat sat on the, and its question is, what's the next word going to be? Yeah. And how does it figure that out? Well, it's looked at a few billion pages of text on the web, and in that particular case, there are probably 10,000 pages where the next word is Matt. So it could just know from the statistics of those pages, I think the next word is going to be Matt. That's what I'm going to put down as the next word. But if it keeps going and you've asked it some prompt it's never seen before, it can't just say, I'm going to look at the statistics of the pages I've actually seen on the web to figure out what the next word is likely to be. It's got to have some other way to figure that out. But still, what it's trying to do is to write words that will be typical of what those pages on the web would have said. And the surprise is that we can make essentially a model of how those words get put together using a neural net. So, neural nets, in the end, it's sort of a very mathematical kind of construct. It's just something, neural nets were invented in 1943, so they're pretty old. And in fact, the neural nets that are in something like ChatGPT are really very similar to the neural nets that were originally imagined in 1943.
This isn't
they are kind of an
Rosenblatt.
idealized model.
This isn't Rosenblatt. This is 43. Who did
that
it?
was McCulloch and Pitts, actually. Warren McCulloch and Walter Pitts. Then Frank Rosenblatt was a bit later with this thing he called the perceptron, which was a kind of a simplified version of the original McCulloch-Pitts idea that he actually implemented in hardware, and that in various versions got used in the 1950s and so on to do sort of basic image recognition kinds of tasks. And the history of this field it's an interesting history because McCulloch and Pitts, Warren McCulloch was a psychiatrist. They were interested in kind of how brains work. And it was known from about 1900 that brains are full of neurons. And neurons are these cells that are they're electrochemical cells where each neuron is connected to maybe 1,000 or maybe 10,000 other neurons. It's kind of like a whole bunch of wires in the brain. And that was known from anatomy back from Ramani Kajal and people like that around 1900. And so there was this kind of, it's like a bunch of wires connected in there. And by that time, by the 1940s, kind of the idea that you could have all these electrical machines with wires and switching networks and so on was a known thing. And what McCulloch and Pitts, so the other thing that had happened was Alan Turing had come along in 1936 and had this idea of a universal machine, had this idea that there could be a fairly simple kind of a mathematically specified computational thing. His original model was a bank clerk who would go and have kind of a filing cabinet, and he would get a page out of the filing cabinet, and then he would write something on that page and then put it back in the filing cabinet and so on. That became the sort of idealized model for computers. And that was so, and the people didn't understand, Turing himself didn't really understand how universal that model would be, to what extent it would be the case that one piece of hardware could be made to do anything just by being fed the right software, which was obviously the thing that's been critical to sort of lots of our modern technology. But so Turing machines had come in 1936. They were somewhat understood. The idea that they could be universal and do arbitrary computations was somewhat understood. 1943, McCulloch and Pitts, their big thing was to show that with a thing made of sort of idealized neurons, you could in principle do Turing machine type computation. Okay, so that was a big thing.
Yeah, yeah.
But then when it got sort of reduced to practice, what neural nets did wasn't terribly exciting. And then my friends Marvin Minsky and Seymour Papert in the 1960s wrote this book about perceptrons, where they kind of figured out a mathematical analysis of neural nets. And the very fact that they could do the mathematical analysis kind of said neural nets don't do anything interesting.
Yeah.
So then people went away and said, okay, neural nets don't do anything interesting. Brains must do something different. We don't know how they work, but it isn't neural nets. Early 1980s, a group of mixture of kind of physicists and some psychology people and cognitive science people and so on sort of got together and started saying, no, actually there's more to neural nets. There can be deep neural nets. Perceptrons tended to be one layer neural nets and so on. And they started figuring out a few things. People like me got interested at that time, tried to make neural nets do things. I didn't manage to get anywhere with them back at the beginning of the 1980s. And then they kind of went to sleep again for many years. And there were a few people working on them. I always found them kind of this sort of strange, mysterious thing where it wasn't clear they were ever going to be that useful. And then, well, to finish the history, actually, in 2011, 2012, the big thing that happened was that a particular deep neural net, sort of almost by chance, it was discovered that it could learn to do image recognition. It could learn to tell a picture of a cat from a picture of a dog. And that was a big surprise. Nobody knew that was going to work. The big surprise, I suppose, was that people thought that a simple toy problem would be easier to do than the big problem of recognizing 5,000 different kinds of visual arts. But it turned out the harder problem was easier to do for reasons that we now sort of understand. And so there's this big jump in neural net capability back in 2012 of it really became useful for doing object recognition. Neural nets have been used for things like optical character recognition for many years earlier than that. But object recognition, this big jump. It's interesting to see that in the time since then, sort of object recognition has gradually gotten a bit better with neural nets, but it hasn't been the same kind of dramatic jump. So then, the big thing that happened last year was this big jump in language generation and language recognition with neural nets. And that's what led to ChatGPT. And I think just to say a little bit more, maybe for people who are interested about sort of how it works, what is a neural net? Well, it's got a bunch of neurons, like ChatGPT has a few million of them. And what is a neuron? A neuron is just it's basically, it stores a number. And then what's happening is that the neural net is, you say there are these layers of neurons, and you're feeding numbers in at the top layer, and then these neurons are connected. One neuron will be connected to many neurons in the previous layer, and it will be connected with certain weights. So all the neuron is doing is basically saying, what were the values of these neurons on the previous layer? Let me multiply those by these weight numbers, add all those results up, and then take some kind of threshold. Like if it's greater than 0, make the result be 1. If it's less than 0, make the result be 0, for example, or something slightly more sophisticated than that. And you're just rippling through a few hundred layers of kind of these numerical computations, and out comes another number or another collection of numbers at the end. So when ChatGPT is doing its thing, what it's doing is it's taken the text that you've fed in, and it's ground that down into numbers. So for example, it might just number different words in English. There are about 50,000 common words in English. It could almost number them. It doesn't quite do this, but more or less it's just assigning a number to each of those words. So it's got this list of numbers that are coming in, which is what it kind of knows so far. And then you take that list of numbers and they ripple through this neural net. And then at the end, you get another list of numbers. And that other list of numbers gives you the probabilities for what the possible next word should be. And then ChatGPT just picks not necessarily the most probable word, but one of the most probable words that were predicted from this neural net, and then says, okay, that's the next word. And then it keeps doing that over and over again. And it's totally remarkable that process can make a reasonable sort of human-like essay.
What makes you think this has anything to do with the process by which humans generate language? I mean, it's a completely different process, and Turing always said that you needed an oracle for your universal Turing machine, that it ultimately depended on an outside intelligence to feed it, and that it couldn't function without this oracle. And why
yes,
do you, and this is a human oracle, why do you think that these ChatGPT neural nets are different from the Turing oracle dependency?
Okay, so I don't think Alan Turing quite said that. I think so Alan Turing did multiple things in his life, so he had different kinds of things he said.
This was late.
What's that?
This was late in his life that he didn't live long.
Right. No, this idea of oracles is actually something that it was actually his PhD thesis was his most obscure piece of work. It was called Systems of Logic Based on Ordinals. And in fact, it was kind of a funny thing because Turing machines, he introduced in 1936, he'd shown that one universal Turing machine was capable of doing the same computation as any other Turing machine.
Right.
You could take that one universal machine and you could, by feeding in different input, you could get it to emulate any other Turing machine. Actually, I have to say, just to add a sort of personal note to that history, I finally figured out what the very simplest possible universal Turing machine could be, and I put up this prize for could somebody prove it, and somebody did in 2007. So we know what the very simplest possible universal Turing machine is. But his idea was that you can have this sort of idealized machine, you can have just one machine, and then you can, by changing how you program it, you can get it to emulate any other machine. He didn't know how universal the universal Turing machine would be. He thought, for example, that physics would be different from that. He thought his universal Turing machine might emulate the way that, like, people do computations or something, but he didn't think it was necessarily the way the universe works. Yeah. What became clear and was a big surprise is that different ways of thinking about what might be the basis of computation all turned out to be equivalent. And then basically in the 1980s, partly through my efforts actually, people began to understand that maybe what had been discovered as this mathematical idealization in Turing machines might apply to physics as well. Yeah. But then Turing, in a rather bizarre kind of, people never really often never believe the paradigms they build. And so Turing really was thinking about this idea of an oracle, which would be a thing that could do problems that a Turing machine couldn't do.
That's like Wolfram Alpha.
What he wrote his What's that?
That's like Wolfram Alpha doing problems that ChatGPT can't do.
Well, yes, except that Alan Turing, in his way of thinking about this, I mean, just to, he was talking about, a Turing machine, for example, can't predict. If you say, what will this Turing machine eventually do even after an infinite time? A Turing machine can't in finite time in general predict that. Yeah. He said, well, imagine that you have this oracle that could predict it. And he wasn't thinking of people. He was thinking of some kind of mathematical idealization. Kurt Gödel, on the other hand, did think that will be about people. Gödel's theorem about mathematics, the incompleteness of mathematics.
What do you think about that?
Well, so that's an equivalent story to universal computation and Turing machines and so on. Kurt Gödel really was, he had this belief that human minds kind of go further than any of these kinds of formal systems. And that was sort of his feeling. I think that the real thing that he was trying to show, and this gets a bit more abstract, is this kind of Platonic view of mathematics, that there's a question of, is mathematics something you just construct? You just say, I've got these axioms, now I'm going to sort of build this structure based on these axioms, or is there a real there to mathematics that we are merely discovering, there's an intrinsic nature to mathematics that we're merely discovering pieces of. And that was a thing which in the early part of the 20th century, there'd been much debate about. And Gödel was very much on the side of, there is a real thing to mathematics. It's not just an arbitrary construct of human minds. And in fact, on that point of what Gödel thought about that, I very firmly agree, although it's kind of a slightly long story, how that emerges from ideas that have come out of our physics project. But the real kind of the soundbite about that is, if you believe the physical universe exists, which is probably a reasonable thing for us to believe, then we have to believe that mathematics in the same sense kind of exists, and that Gödel was really right about that. But Gödel none of these people knew at the time what, they had made these simple idealized models. They didn't know how accurate they would be about brains. And I think that the question is, when we have brains and we've got our 100 billion neurons in our brains, and they're connected in all these ways, and they have all these electrical signals that are being produced and so on, what aspects of that actually matter? If you want to do brain-like things, it's kind of like you have a bird. A bird has feathers. A bird has, flapping wings and so on. Which aspects of that matter if you want to fly? And it turns out the fact that you have wings seems to matter. Well, unless you're a drone of some kind. But there's some things that matter, but other things don't. Feathers don't matter. We don't have feathered airplanes.
So going back,
and so this
Stephen,
question of what matters in brains is a science question, basically. And what I think we're learning is that for purposes of generating language, what matters isn't the details of the fact that our neurons consume glucose and things like this. It's the overall architecture of brains. And, to the question of whether, what a ChatGPT can do versus what it can't do, I think that what brains do quickly is a good model for what it can do. In other words, the things that we can do, the details of how our neural network in our brains works as compared to the neural net that's in ChatGPT, we don't know how that corresponds. We don't know how close that is. People in neuroscience had believed that these artificial neural nets were actually pretty far away from the way that biological ones work. Although having seen what the artificial ones can do, it's been realized that they're actually closer to the biological ones we thought.
So if we gave them
it's actually very much...
Stephen, so if we gave them a quadrillion parameters, these neural nets, gave them a quadrillion, would that yield AGI?
Well, I think we have to define what we mean by AGI. I think the thing to understand is the task that they're doing, which is complete this piece of text, is a very definite task. It's a task that's very, very important for us humans. It's very relevant for us humans. It's not the only thing you can do. I mean, basically, the thing that it denies is kind of the formalization of the world. It denies kind of all of modern science. It's like what the unaided human can do, it has a chance to do. But we humans have invented these methods like computation, like mathematics and so on, that allow us to formalize things and allow things to be done that are beyond what we can just sort of run in our brains. And that, that's not what ChatGPT does. ChatGPT is this thing that emulates the kind of linguistic aspects of sort of knitting words together, and we can discuss how it manages to do that.
By collecting vast quantities of statistics, which is a radically different way from the way human brains master language. I think it's...
I don't think we know that.
We don't get a trillion internet data points to generate the next word in the sentence that we may use.
So the GPT told me that 2 + 2 = 5. And
it will do all kinds of crazy things. Right, so I mean, look, first point is, in terms of the amount of experience that exists in the training, we talked about neural nets and sort of this idea of training neural nets is about, can we make all these weights, can we tweak them so that the answers will agree with kind of what would be typical of like documents on the web. So for example, when we were first training image recognition networks, after the sort of big advance that was made, we were training some back in 2013, 2012 or so. And I was kind of curious, how does the number of training samples that we had compare to the number of number of different images that a child sees in the first couple of years of life? And we had, I think, 20 million training images. And that's kind of comparable to what a typical kid sees in the first couple of years of life. So in that particular case, it was sort of comparable. I think in the case of ChatGPT, well, I know, I personally have put 50 million words out there into the world. Okay, so 50 million words, the total training corpus is around 1 trillion words now. So my 50 million words is just kind of a drop in the bucket. I probably heard a lot more than 50 million words. But yes, it's not quite the same number. And in fact, I think it's probably true that the hardware in our brains, there's probably some hardware which is maybe better suited to human language than what we yet know how to build with ChatGPT. There's some even hardware aspects where we kind of know it's inefficient in what it's doing relative. Right. I mean, okay, brains, for example, here's a very basic thing. In a computer, there's memory and there's CPU. And most of the time, the memory is doing nothing. And most of the time, it's just sitting there, storing data. And, that's what's happening with ChatGPT. Most of the time, the network, which is, stored in memory, is not changing. In our brains, the neurons are both being used to actually compute the next word, so to speak, and being used and being able to learn continuously. That's something we don't yet have hardware that does, but we probably will have. But so I think that's some. But let's see. We were talking about. Bob was asking about the quadrillion parameter, GPT system and what will it do? And I think well, first of all, we're really at the edge of the training data that we humans have put out there. I mean, we put, maybe 10 billion web pages that are somewhat sensible. If you look at like the biggest collections, the archive collections of the web, maybe a couple of hundred billion pages. Nobody even knows how repetitive those are. But that's what we humans have put out there. We put out there a lot of video and things like that as well. But that's kind of the corpus of human kind of language that these systems can learn from. In terms of, it doesn't do much good to have lots more weights, lots more neurons if you don't have more to train on. And I think the thing that you might ask is, well, could it be the case that this quadrillion, neural net has another qualitatively new kind of ability to do things beyond what we see in the existing LLMs? I have to say I'm not optimistic about that. I think that I think what we've seen is the big jump in terms of language capability. We'll see another jump when video capability becomes sort of gets into the picture. But I think we've seen that big jump. Now, when you talk about AGI, it's a muddy word, a muddy term, I think, because it's kind of like you say, okay, Bob certainly knows that in the history of kind of the last, I don't know, I've only seen it for 50 years, but he's seen it for more than that. What people mean by AI, whenever there's stuff computers can't do and humans can more or less do, that's in the AI bucket. When we can do that, we know we have AI. And so people have said that about, or even doing mathematical computation, people said that's when we can do that, we'll know we have AI. And then progressively, each of these things that is like, oh, only humans can do that. To do that, if we could do that, we really know we had AI.
So what do you hope?
It keeps on getting done by essentially pure engineering.
What do you hope to accomplish by putting Wolfram language underneath ChatGPT?
Okay, but just to finish this thought about kind of. Well, okay. Maybe we move to that. I mean,
I'm sorry. I did not change topics. The question I just asked, 2 + 2 = 4, is something that Wolfram language can teach this entity, and without it, it's beyond human. It's beyond human capability. It's beyond the capability of the neural net to do arithmetic, right?
Right. Well, I mean, a neural net can look, what a neural net does is it produces things that are linguistically plausible. They may be total nonsense, but they are linguistically plausible. You know, it'll produce a collection of academic looking references that look right. They may not actually be right. So that's, you know, it's doing its kind of pattern matching and finding kind of what looks right. Now, we have this other approach, which is this much more formal approach where we can actually say, we know step by step, we apply these rules, we get the answer, and it's right. Yeah. And that's what we've been concentrating on in building out Wolfram language, Wolfram Alpha, and so on, is curating data from the world, figuring out these ways to sort of precisely and formally set things up so that we actually can sort of get the right answer. And so you know, for us humans, we don't expect to be able to run a piece of code in our brains. We expect to use a computer to run that code. Yeah. And so it is with the AIs. So it is with these neural nets. That's what we're able to do there is use Wolfram language as a tool and have the neural net sort of be a linguistic interface to that, be something where we as humans can sort of talk to it linguistically, and then it turns that into something that can be stated in this precise computational language. Right. We can then do the computation, bring back the result, and then the LLM can write an essay about it. It's really it's a kind of a different direction. I mean, this idea of formalized computation is really a different direction than this idea of kind of statistical sort of follow the you know, what you would expect from the web, so to speak, to fill things in with. Right. And so, you know, the combination is really powerful. And I think, you know, when you ask, will the neural net get to the point where it is able to do those kinds of things? I don't think any more so than humans will get to the point where they can run code in their brains, so to speak. I don't think that's a limitation of the number of neurons we have in our brain. I think it's just the nature of the way that brains are set up as compared to this much more sort of formal structure, which we could define even independent of the computer. I mean, it's much easier to define what it means to have a correct computation than it is to have a, you know, correct result from an LLM. We don't know what a correct result is. You know, I think the thing to realize about what the LLM is showing us is that what is it really doing? I mean, it's completing sentences in a way that is appropriate based on what typical meanings are in language. And I think, you know, the way I like to think about it is we've known for a long time that there's sort of a syntactic grammar of language. We know that sentences are constructed with noun, verb, noun, things like this. Knowing that sentences go noun, verb, noun doesn't mean that will make sentences that mean anything. Yeah, right. We could write, you know, the green electron happily went to the store. Doesn't really mean anything, except in some bizarre poetic sense. But it's grammatically correct. It's syntactically correct. What I think ChatGPT is kind of showing us is that there's another level of kind of construction kit for language, which is kind of a meaning-based construction kit, where we have all of these different ways that we can fit words and so on together in order that they have some meaning. Yeah. That meaning may or may not be correct in this formal sense, but it at least is not, it is sort of typical of the way we use these words. Yeah. So for me, I mean, at a very practical level, the what I see in kind of the LLM world, and we've been doing a lot of integrating of LLMs with Wolfram language, this sort of combination of the linguistic interface together with hard computation is super powerful. Whenever you're using this linguistic interface, it's kind of a somewhat hit and miss thing. Like a lot of machine learning, any use case where getting it 80% right is a win, it's going to be good. If your use case is we got to get it 100%, it's got to be exactly right, or it's useless, or our rocket is going to blow up, or whatever else, then it's not a good use for an LLM.
Or the electric car will crash, or
yeah, right.
Gentlemen,
that's not a good use for the. I mean, you know, that's a complicated case which we can talk about separately. But that's the issue tends to be, you know, if you're generating, for example, let's say you're writing computational language, and you write something, you know, you type some text in, and it then produces this piece of computational language. If it gets it right, and you can see it gets it right, you're very happy. Off you go, you use that. If it gets it wrong, you say, oh, let me try and fix it, or let me complain to it and it'll try and fix it. And maybe you'll iterate and get it right, or maybe you'll say, forget it, I'm not going to use the LLM, I'm just going to write this computational language code myself.
It's
But
an oracle,
it's still,
Stephen.
Gentlemen, we have about 6 or 7 minutes left, so maybe some concluding remarks. And Stephen has very kindly joined us during his own conference, so thank you for that, Dr. Wolfram.
Thank you, Stephen.
And so just a few closing remarks, and then we'll wrap up at 3:30 our time. Thanks.
Future of AI. And the input-output problem. I mean, the I/O problem, which really hasn't been addressed in something like ChatGPT. The input is just internet data, which is not comparable to the human sensory integrative systems that actually generate speech and understanding and correct answers in human beings. So my feeling,
sorry.
So
No, I mean, one of the things when people talk about AGI, a lot of what happens is, in the end, the only thing that's going to really qualify is basically a human. In other words, it's got to have, in the end, it's got to have, it's got to be able to experience the environment, it's got to be able to walk around, it's got to be able to have, emotions, it's got to have this, that, and the other. And in the end, you've got something which is essentially a copy of a human. And even you've got to start thinking about, when you think about its sort of bigger arc, you've got to start thinking about mortality and about, its inner feelings and so on. And in the end, to have the thing that's truly going to qualify as what I think people imagine AGI to be, it's going to be something that is basically a human. So when you think about the sort of the digital version of that, one of the things people wonder about is, okay, what are the AIs going to do when AIs rule the world, so to speak? What will they do? And one of the things to realize is an AI has no intrinsic, unlike humans who feel like they have intrinsic motivation to do this or that thing. An AI is just set up to kind of do its computation, and it has no, it doesn't have a goal, so to speak. It just does what it does.
All numbers.
What's that?
Numbers. It's a symbol system.
Yeah,
it's a symbol system. And as Charles Peirce saw, symbol systems are not connected to the real world except through interpretants. And those interpretants are human minds. And you think eventually that somehow AI will transcend this need for an interpretant. It somehow can eclipse the interpretant and connect the symbol to the reality in some direct and
No, I actually don't think that.
Okay.
In fact, I think that the kind of the abstract notion of computation is both rich and barren. It's rich in the sense that there are many possibilities, many that we don't care about yet. There are all these things that can happen in the computational universe, and we look at them and we say, we don't know why we care about that. That's one thing. The other thing is that, so there's a lot going on in the computational universe far beyond what we humans have ever thought about. On the other hand, the part that is important to us is the part that's very directly connected to us. In other words, the kind of the version of AI, when we imagine all these AIs going off and doing all the things they could do, it's kind of like the natural world, where we've got all these systems in the natural world that are going off and doing what they do, but the question of what aspect of that we care about depends on how we connect to all of that. So in the end, I really think that humans, sort of what's relevant to us is something that is very connected to humans, where humans are really at the center of the whole story. And what is computationally possible is this sort of vast range of things, but the only part we care about is the part that's connected to us humans. There's something that comes out very clearly in this whole sort of development in science that we've been doing. But I think, it's like people say, well, what will the AIs do? If the AIs rule the world, what will they all do? Well, can just do arbitrary computations where we say they're just doing computations like nature does computations, and we kind of shrug our shoulders and say we don't know why we care about that. It's only the things that kind of connect to what we humans are interested in that we really care about. So I think humans. I think you're right. I wouldn't. It would be an interesting discussion how this relates to Peirce's ideas about pragmatics and all this kind of thing. But I think that this idea that for what we care about, we humans are very much at the center of it. What is computationally possible goes far beyond us humans.
Yeah, right.
George,
But what is computationally possible, just like what is possible in the natural world, is a lot of things that we just don't care about. Yeah. It is not part of our experience of life, our goals in life, and so on, to engage with those things. Yeah. And what we're doing is we sort of pull out of this computational universe the aspects of computation that we care about. That's kind of the story of, I think, our kind of how we should think about AI, and the kind of the sort of the ultimate AI can do any computation it wants is both. It's both bigger than us and irrelevant to us.
And it doesn't want anything.
What I think
George, will
and
you?
It doesn't have wants, does it?
We'll make this the concluding
doesn't
word.
have what, sorry?
Doesn't have wants. It doesn't want to do any computation.
Yes.
It has capabilities.
Right. But exactly. I mean, this is the weird thing, and this is where we get into all sorts of philosophical issues. Yeah. All of us feel internally that we have wants. Whether we know what the feeling of anybody else is just an extrapolation from what we internally feel. Yeah. And this question of whether we will extrapolate to think that the AI has wants, just as we extrapolate, because the only feeling that we have intrinsically is our own feeling, so to speak. Yeah. And we can extrapolate to other humans. We could imagine extrapolating to AIs as well, that sort of act like humans. But yes, in some, I mean, ultimately, the only thing that we kind of really intrinsically know about is what's happening inside us. Yeah. And that's something that, we have learnt to kind of extrapolate to other humans. Yeah. But I think that's I think it is true that the inner life of the AI, so to speak, is only known to the AI, just as the inner life of a human is only known to that human. Yeah. So I think it's a philosophically quite complicated thing. And by the way, that philosophical issue, I think, is at the heart of a lot of AI ethics questions, because this whole question about whether AIs seem different from humans, partly because they don't have these same kind of wants that humans have, or we don't perceive them to have those wants. And part of the reason is because we can say, look, we can look inside the AI, we can see it's just a bunch of neural net, neurons with numbers in them and so on. So that means it's not really doing anything that is sort of, it's just a bunch of numbers flapping around.
Dr. Wolfram.
Of course, what we have to realize is for our brains, it's the same story. As we get to be able to sense more, we will see that those 100 billion neurons in our brains are also just following certain rules and doing what they do. And yet we have the inner feeling that there's something more significant than that. And it sounds like we should wrap up there.
Well, Dr. Wolfram, that was a wonderful concluding word. So let's give him a round of applause.